Hello, friends. Welcome back to the Quantum Night. Today, we're going to be talking about rocks, and that rules. Now, of course, this is a physics channel. We mainly talk about physics here, but rocks can be very important, especially when we're talking about particle physics experiments. Now, why might that be the case? Well, when we're talking about particle physics, we're talking about very small particles. We're examining protons, protons, neutrons in nuclear physics, but for particle physics, it's more elementary particles, quarks, which make up those protons, electrons, even neutrinos. And the thing is, those very small particles, there are a lot of those elsewhere in the universe. Most notably, they are produced by events, radiation events, or fusion and fission. And where is the big source of that in our solar system? The sun. So essentially, the sun is this big source of particles that essentially make up cosmic radiation that stream towards our planet. And when we do our experiments, sometimes we want to not have all that extra particle stream um, running through our instruments and our detectors because it will produce a lot of background that we'll need to remove. However, when we also use rocks to block that radiation, there can be downsides that impact our experiments. So we're going to do a short little talk here about some types of particle physics experiments, why we would use certain rocks, and then, of course, what sort of things you need to keep in mind when it comes to rocks in your experiments. All right, so when it comes to particle physics, there are essentially two types of experiments that we do. There are um, experiments where we try to produce these particles. Think the Large Hadron Collider, where we go ahead and accelerate a bunch of particles to really, really high speeds, and then we take them and we smash them together, and boom, you get all sorts of junk that comes out. And that junk is the particles that we're looking for. And we have a bunch of experiments at those collision points that read the data. Now, there are also experiments that want to just sort of look for data. So, for example, you can go ahead and have if we're interested in dark matter, we might not be making dark matter. We might not be able to make dark matter in these particle collisions, but there is dark matter in the universe. We're aware of that. We have been able to observe it. So, if we make these big detector balls or big areas and we let the dark matter in the universe end up sort of passing through our detector, we can hopefully detect it. For example, a good one that I use is Snow Lab, or the Snow Experiment, which is located now at Snow Labs in Sudbury, Ontario, Canada. It is a giant ball of. It used to be heavy water. I think it's now. No, it might still be heavy water. Big ball of heavy water with a bunch of photomultiplier tubes, essentially these tubes that look for light. And when the desired particles go through it, they were doing neutrino analysis, and the phenomenon that they were looking for occurs, it produces light, and that light can be detected. Okay, so with that in mind, we've got our two types of experiments. Now, at experiments where we produce a bunch of data, we produce a bunch of particles in these collisions. Why would we want rocks? Well, so at the LHC, we have the beam. I think it's about 100 meters under the ground, pretty deep. And part of that is due to the fact that when you produce a collision, you can get a bunch of particles that last a very long time and some that don't. And some of those can permeate through rocks for a large distance, while others can't. And by having that level of rock, it can prevent the spread of the radiation that is produced. It also shields out that cosmic radiation to a certain extent. So the detector might not have to deal with problems of particles traveling through it. This is less of an issue for this sort of experiment, though, because we know that what we're going to be producing is going to come from the center of that beam where they smash out. So it's going to come from one singular point. And often in these sort of experiments, we've got multiple layers of detectors. And so those layers can ping, the particle went from this direction, versus the particle comes from this direction. We can sort of cut out that excess stuff. So it's a little bit of shielding and a little bit of protection. Rock is far much more important in the second type that we talked about, those big stationary detectors. So we're going to talk about, I'm going to use DEEP as an example. I did a little bit of research in my undergrad on DEEP, and DEEP was an experiment that was being done at the university that I was at. So DEEP 3600 is a dark matter experiment located at Snow Labs in Canada. It is a dark matter detector that uses liquid argon. So I think it's like a meter, maybe a meter and a half sized ball of liquid argon with a bunch of these photomultiplier tubes. And the idea is, well, okay, if dark matter travels through, it might interact with this liquid argon if it's a type of dark matter that we think it might be or that this detector is designed to look for. And detecting dark matter and those parameters might be a fun little thing to talk about. So if you want to hear about that, leave that down in the comments. But we have, we want to have a certain interaction that produces these the light that our photomultiplier tubes can observe, and then we ping that off and go, dark matter, woo, that's fantastic. But the thing is, with that solar radiation coming through will look sort of like just dark matter coming through the detector's bulb, or can, right? The particles coming from it, if they interact in the right way, could do that. So what we want to do is cut out that radiation. Best way to do that, put it underground. Snow Labs is located, I think it's a kilometer or 1.5 kilometers under the Earth crust. Under the ground. It's in the crust. Actually, it's not very far in the crust, really. Anyways, that's a geological question, not a physics question. We're here to talk physics. So, down underground, most of that radiation that comes from the sun or comes from space, because there are other things in space that produce radiation, can get shielded against, and so it doesn't come down and really interfere. But we do expect dark matter to make it through because dark matter doesn't interact with normal matter, so it shouldn't really be affected by that rock. It should be able to travel right through. Now, of course, when we deal with rock, we have the problem of the fact that rock is made up of many elements and minerals. Minerals are made up of elements. And the thing is, the atoms that make up those molecules can potentially be isotopes. They could potentially be made up of things that aren't stable. So what is an isotope? An isotope is a type of atom, right? We can talk about carbon. An isotope of carbon might have more neutrons than usual carbon has, or less neutrons than common carbon. And certain particles in certain isotopes are less stable, and they will eventually decay and produce radiation. This radiation is usually ionizing radiation, which means it's alpha particles, beta particles, or gamma particles. Gamma particles is light. They're just photons. Alphas and betas are proton and hydrogen nucleus. Some helium nucleus. Helium nucleus, and I believe it's it's an electron. Electron or a helium nucleus. So point stands, they can produce radiation. This radiation is just high moving, high energy particles traveling out from the material. Most notably in rocks, the biggest sources of radiation come from uranium and thorium. Uranium, you probably know it because, well, it's famous for that. Thorium is also very radioactive and can decay. Now, usually rocks don't have very high quantities of these. They spread out, but they do exist. It's actually a really cool tool that we can use to measure the age of rocks. But that's besides the point. Essentially, this uranium or thorium might produce some sort of radiation. That radiation can be produced in that rock layer. So let's say we're deep underground in the mine shaft. Well, in this mine, the walls are made out of granite, like this piece of granite here. This is a very feldspar heavy chunk of granite I own. Let's see if I can get a good view of that granite. Look at that beauty. All right. Well, granite commonly is one of the bigger sources for finding for having uranium or thorium in it. And so that uranium isotope decays, and that decay produces a beta particle. And the beta particle might go down and interact with the argon, an atom of argon in the liquid argon, and that might produce it, would cause it to become excited. When it gets excited, it has a bunch of energy increase, and then it goes back to its normal state, or it releases all that energy that it's gained as light. And the light that it produces might be at the same low level that we expect the light that would be produced by an interaction with dark matter. So that can be an issue. That is one of the biggest sources of background that a lot of these underground experiments have to deal with. They have to deal with the fact that, we can have this radiation can interact with points, and that can potentially look like an event that we're looking for. So we need to be able to remove these. One that I worked on, actually, when I worked on DEEP in my second year of my undergrad, my job was to go ahead and take the, we had alpha particles interacting with the neck of the detector. So the best way to think about DEEP is it's a ball, but because it's made out of, it has cryogenic liquid argon in it, that liquid argon will eventually heat up and it will turn into gas. So we need to be able to cool that down. So there's this big pipe that comes up from the ball, and in that pipe is the cryogenic pieces that cool it down. So it would cool it down, and then it would drip down through the pipe, or it was called the neck, through the neck back into the main core. Well, if there was an alpha particle that interacted in the neck, that alpha particle could produce a photon that, if partially covered by pieces of the neck, would make it appear to have the energy of a dark matter event in the middle of the detector. What we would do to remove that would be to consider the fact that, we can kind of reference where our flash came from. Because it's a big sphere, you got a bunch of little cylinders around the side, little reading points around the side. If you have something in the middle, well, you should be able to get sort of a readout to a number of them, and you can kind of trace, when did the readout come in, to kind of measure the distance it is from everything. If it's up in this neck, a bunch of them aren't going to get a reading for it, and then that means, okay, we have an event in our neck. We just need to remove that. So yeah, now you understand kind of why a bunch of these experiments are deep underground. It can be a little bit confusing, but it's very interesting. Another thing we didn't talk about is the fact that you can use these for their own analyses as well. For example, at ATLAS, we have, or not at, well, at the Large Hadron Collider, where ATLAS is, one of the things they do is they get the beam going, they collide the beam in sections, and then eventually they have to do beam dumps. They have to dump this beam of high energy protons out of the collider. So they do this into a big chunk of rock in the Alps. And actually, there are experiments on the other side of the Alps that looked for interesting readings to see what stuff might have made it through the rock. After all, the rock can shield a bunch of things, but if we see something interesting coming through it, that can be noteworthy. Most famous of that, I believe, was there was a time where a group thought that they measured neutrinos traveling faster than light, and it was a calculation error, but I believe they were one of the groups that does that. All right, so now that you understand rocks and physics, I guess you know why physics rocks. All right, if you enjoyed this content, please like and subscribe. Hopefully the green screen will get better and better in each video, and eventually it will be used properly. All right, take care of yourselves, and I'll see you next time. Bye bye.